the silent echo of the universe. What if I told you that right now, all around you, there's a whisper from the very beginning of time? It's not a myth. It's not science fiction. It's real. A faint signal that fills the entire cosmos, stretching across space and time, older than the oldest star, older than the galaxies, older even than atoms themselves. A glow, invisible to the naked eye, that scientists call the cosmic microwave background, or CMB. Discovered by accident, misunderstood at first, but ultimately it changed everything we thought we knew about the birth of the universe. In this video, we're going to dive deep into the astonishing story of the CMB, the ancient light from the infant universe. We'll see how it was discovered, what secrets it holds, and how it became one of the most compelling pieces of evidence for the Big Bang. And if you stay with me till the end, you'll also learn how tiny fluctuations in this background light help shape everything, from galaxies to the very atoms in your body. Because the CMB is not just an echo, it's a cosmic memory. And if we know how to listen, it speaks. Moments after the beginning to understand the cosmic microwave background, we first need to travel back, not just billions of years, but to the very first few minutes after the universe began. The event we call the Big Bang wasn't an explosion in space. It was an explosion of space itself, the sudden expansion of all matter, energy, time, and space from a single, unimaginably hot and dense point in those first few seconds. The universe was blindingly hot, trillions of degrees, so hot, in fact, that atoms couldn't even exist. It was a chaotic soup of quarks, electrons, neutrinos, and photons, light particles, bouncing and smashing into each other in a dense plasma. This early universe was opaque. Imagine trying to see through the thickest fog you can imagine. But worse, they were constantly scattered by the dense cloud of free electrons. It was as if the universe had no transparency at all. You couldn't see through it, not even an inch. Photons, the particles of light, couldn't travel freely. But the universe didn't stay that way. As it expanded, it cooled down. And about 380,000 years after the Big Bang, it reached a temperature where electrons could finally combine with protons to form neutral hydrogen atoms. This moment is known as recombination, and something incredible happened. With the electrons locked inside atoms, photons were finally free to travel. Light, for the first time in history, could move unimpeded across the universe, and it has been doing so ever since. That ancient light is the cosmic microwave background. It's not visible to our eyes, because the expansion of the universe has stretched its wavelength down to the microwave range. But it's still there, glowing faintly in every direction of the sky, carrying with it the snapshot of the universe as it was at that exact moment. Think of it as the baby photo of the cosmos. And in this photo, every tiny ripple and color variation contains clues about how stars, galaxies, and eventually life itself would form. But the CMB might never have been discovered at all, if not for a pair of engineers trying to solve a very different kind of problem. The accidental discovery of a 13.8 billion-year-old signal, the static that changed everything. In the early 1960s, to radio engineers at Bell Labs, Arno Penzias and Robert Wilson were working on something completely unrelated to cosmology. They were trying to calibrate a very sensitive microwave antenna designed for satellite communications. It was a state-of-the-art device, precise and capable of detecting even the faintest radio signals from space. But there was a problem, a strange background noise. No matter where they pointed the antenna, toward the city, away from it, straight up into space, they kept hearing a persistent, low-level hiss. It wasn't coming from Earth. It wasn't from the Sun or the Milky Way. And it wasn't a mechanical glitch. They even cleaned out a nest of pigeons that had been living inside the antenna and removed all their droppings, just in case. But the noise remained. That mysterious static was coming from every direction in the sky, equally strong. What Penzias and Wilson didn't know was that, just across town at Princeton University, A team of physicists led by Robert Dicke have been working on a theory. They believe that if the universe began with a Big Bang, then the afterglow of that event should still be detectable, not as visible light, but as microwave radiation. In a twist of fate, the two teams connected. When Dicke's team heard about the strange signal Penzias and Wilson had found, Dicke reportedly turned to his colleagues and said, "Well, boys, we've been scooped." Penzias and Wilson had accidentally discovered the very thing the Princeton physicists had predicted, the cosmic microwave background radiation, or CMB. It confirmed that the universe had a hot, dense beginning, and that we could still detect its glow today. Their discovery, published in 1965, provided the first direct evidence that the Big Bang really happened. For this groundbreaking work, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978, but that discovery was only the beginning, because once we knew the CMB existed, the next question was, what could we learn from it? That brings us to the next chapter, where we zoom in on the CMB, pixel by pixel, to uncover secrets about the birth of galaxies, dark matter, and the shape of space itself. The universe's first imprint. Once scientists confirmed the existence of the cosmic microwave background CMB, they turned their attention to a crucial question. Was the CMB perfectly uniform, or were there tiny variations hidden in its glow? At first glance, the CMB seems incredibly smooth, the same temperature in all directions, about 0.7 to 5 Kelvin above absolute zero. But the early universe couldn't have been perfectly uniform, or we wouldn't be here. Galaxies, stars, and planets, all of them required clumps of matter to form. If everything had started exactly evenly distributed, gravity would have had nothing to work with. These would be the fingerprints of quantum fluctuations that had been stretched by inflation, seeding the structure of the universe. So scientists searched for anisotropies, tiny fluctuations in the temperature of the CMB. These were the seeds from which galaxies would grow. And finally, in 1992, NASA's COBE Cosmic Background Explorer satellite delivered the answer. It showed minute variations in the CMB differences of just 1 part in 100,000, confirming that the early universe had tiny ripples in density. Stephen Hawking called this result the greatest discovery of the century, if not of all time. But COBE's resolution was limited. To really see the structure of the early universe, we needed better eyes. That came in the form of 2 missions, WMAP Wilkinson Microwave Anisotropy Probe, launched in 2001, Planck satellite, launched by the European Space Agency in 2009. These missions mapped the CMB in exquisite detail, creating a full sky map of the early universe, like a baby photo taken when the cosmos was only 380,000 years old. What did these maps reveal? Regions slightly hotter and cooler, due to density differences, clues about the total matter and energy content of the universe. By analyzing it, scientists can test theories of inflation, measure the Hubble constant, and even refine the age of the universe, 13.8 billion years. Evidence for dark matter and dark energy, and how they shape the cosmic web that holds our universe together, even the geometry of the universe, showing it as flat on large scales. Each pixel in the CMB map holds precise data about the universe's birth conditions. The image of the CMB became one of the most important scientific photographs ever taken, not because of how it looked, but because of what it told us. The next big step, we'll journey into what these tiny variations, these cold spots and hot spots, actually mean. From quantum fluctuations to galaxies, imagine the early universe, filled with a nearly uniform plasma of particles and radiation, just after the CMB was released. Now picture this smooth sea being ever so slightly disturbed by tiny fluctuations in temperature and density, as revealed by COBE, WMAP, and Planck. These small ripples, just 1 part in 100,000, were not random noise. They were quantum fluctuations, stretched to cosmic scales by inflation, and now frozen into the structure of the universe. But how did these tiny differences evolve into galaxies, clusters, and vast cosmic structures? Here's the answer: gravity. Regions with just a little more matter pulled in even more matter. Hotter spots expanded slightly faster, while cooler, denser regions collapsed under their own gravity over billions of years. Gravity acted on those slight overdensities. This process, called gravitational instability, led to a remarkable transformation. The cold spots in the CMB became the seeds of galaxy clusters. The hot spots became the less dense voids between them. Using computer simulations, cosmologists have recreated this evolution, showing how the early fluctuations formed a vast cosmic web, an interconnected structure of. It determines how galaxies are distributed, how they evolve, and even how light travels across space. Filaments, thin threads of galaxies stretching across hundreds of millions of light years. It's like the universe followed a blueprint written when it was only 380,000 years old. Nodes, intersections of filaments that became superclusters, voids, massive empty spaces between the threads. This web is not just beautiful, it's essential, and incredibly, the pattern we see today. This immense web matches the patterns imprinted in the CMB. Observations of the CMB and large-scale structure now tell us, and why that has sparked one of the greatest scientific mysteries of our time: the Hubble tension. Only 5% of the universe is normal matter, around 27% is dark matter, which shape the cosmic web, and 68% is dark energy, driving the universe's accelerated expansion. So when you look up at the night sky and see the stars, remember their positions, their clusters, even the gaps between them, were all written in the faint microwave whispers left behind billions of years ago. And that leads us to one final, mind-bending revelation. In the next part, we'll explore how the CMB helps us measure not just what the universe is made of, but how fast it is expanding. Why doesn't the universe agree on its own expansion rate? For nearly a century, we've known the universe is expanding, a discovery made by Edwin Hubble when he observed distant galaxies moving away from us. This expansion is described by the Hubble constant H's, a number that tells us how fast the universe is stretching per megaparsec of distance. But here's the shocking part. Different methods of measuring the Hubble constant give very different answers. Method 1. The early universe, using the CMB satellites. Like Planck analyzed the temperature fluctuations and patterns to infer the physics of the early cosmos, including its composition, density, and curvature. Cosmologists use the CMB as a snapshot of the infant universe. From this data, using the CDM model lambda cold dark matter, scientists predict how fast the universe should be expanding today. The result: H is approximately equals 67.4 kilometers per second MPC. What happens when we directly measure the current expansion? Planck collaboration, 2018, but this is just a prediction. Method 2. The local universe, measuring supernovae, gives a direct observation of the current expansion rate. Astronomers like Adam Maurice and his team use Cepheid variable stars and Typeus supernovae, known as standard candles, to measure actual distances and redshifts in nearby galaxies. Their result: H approximately equals 73.0 kilometers per second MPC. As HOES team, 2019-2023 CMB-based prediction and the late universe, supernova-based observation. That's not just a small discrepancy. It's more than 5 sigma apart, meaning the probability it's due to random error is less than 1 in a million. This is what scientists now call the Hubble tension, a conflict between the early universe. Why is this such a big deal? Because it might mean that something in our current cosmological model is missing or wrong. Some proposed explanations include early dark energy, a brief period of extra repulsive force. Just before recombination, the entire disagreement centers around what the CMB tells us about the early universe and how we compare it to the universe today. New neutrino physics, perhaps more neutrino species, or mass than expected modified gravity. General relativity may not fully apply at cosmic scales. Systematic errors. Maybe there's a flaw in how we calibrate distances. But none of these fully resolve the tension yet. And here's where the CMB comes in again. It sets the stage. It's a cosmic detective story with two witnesses giving different testimonies, and both seem trustworthy. In the next section, we'll explore how new missions like James Webb, Euclid, and CMBS might finally help us resolve this tension or uncover new physics entirely. Unanswered questions in the light of the ancient cosmos. The cosmic microwave background CMB has illuminated many of our deepest cosmological questions, but it has also raised new ones, leaving scientists on the edge of what we know and what we don't. Let us explore some of the most intriguing mysteries that continue to challenge our understanding of the universe. 1. Why is the universe so uniform? Even regions of the CMB that are separated by vast distances, too far apart to have ever communicated, have nearly the same temperature to 0.7 to 5 K. This is known as the horizon problem, but we still don't know what caused inflation, or what fields or particles drove it. Inflation offers a solution, a rapid expansion that stretched out early quantum fluctuations, evening out temperatures. Could it be a quantum field we haven't discovered yet? Or is our understanding of space-time itself incomplete? But there are hints of curvature in certain data sets, especially when combining CMB data with gravitational lensing or large-scale structure. To what is the geometry of the universe? The CMB helps us infer the overall shape of the universe, whether it's flat, closed, or open. So far, observations point to a flat universe, meaning parallel lines never converge or diverge, or just statistical noise. Could this be a clue toward higher dimensional geometry? 3. Is the cold spot a fluke or a portal? Among the tiny fluctuations in the CMB, one anomaly stands out: the cold spot. Located in the southern hemisphere of the sky, it's a region that's significantly cooler than the surrounding areas, and larger than expected. Some think it could be caused by a giant supervoid, an unusually empty part of the universe. Others speculate it could hint at something far stranger: a collision with another bubble universe in a multiverse, a quantum fluctuation from before inflation. But we don't know what dark energy is. A cosmological constant, a new field like quintessence, a breakdown in our theory of gravity, even hints of new physics beyond the standard model. No theory has been confirmed, but the mystery remains. 4. What is dark energy really made of? The CMB, combined with other observations, tells us the universe is not just expanding, it's accelerating. This acceleration is driven by dark energy, which makes up about 68% of the universe. CMB data helps constrain its behavior, but we're still flying blind in a universe dominated by the unknowns. 5. Is the universe the same everywhere? The cosmological principle that the universe is homogeneous and isotropic on large scales underpins all of modern cosmology. But some features in the CMB challenge this: the axis of evil, a strange alignment of low order, multipoles to polar asymmetry. One half of the sky has slightly stronger fluctuations than the other. Are these just statistical anomalies, or signs of new symmetries, or broken ones in the early cosmos? 6. Did something come before the Big Bang? The CMB is the earliest light we can see, but not the beginning of everything. Before recombination, before inflation, what happened? Some theories suggest a bounce, a universe that collapsed and re-expanded. String cosmology, higher dimensions curled in on themselves. The multiverse, infinite births of bubble universes. While the CMB doesn't directly answer these questions, its patterns might contain subtle fingerprints, echoes from before time as we know it. 7. What new tools will reveal more? And reflect, why does the CMB matter so much, not just to scientists, but to all of us? Why does this ancient light still speak to the human spirit? The next generation of observatories could help crack these mysteries. But like all great maps, it doesn't just tell us where we are. It hints at how much more there is to discover. CMB-S4, a ground-based telescope array designed for ultra-precise measurements of polarization. Lightbird JAXA, ESA, focused on primordial B modes, seeking direct signs of inflation. Simon's Observatory and South Pole Telescope, pushing the limits of resolution and sensitivity together. They aim to refine, challenge, and maybe even replace our current models. The CMB gave us a map of the baby universe. In the final part of this video, we'll step back. How we observe the past with CMB Light. If we look deep enough into space, we're not just seeing far-off galaxies, we're literally looking back in time. And when we peer far enough, we encounter something astonishing. The cosmic microwave background CMB, the oldest light in the universe. When the universe was just 380,000 years old, it became transparent for the first time. With sensitive microwave telescopes like the Planck satellite, scientists have mapped this light in exquisite detail. The CMB effectively acts like a time capsule, frozen in space, preserving the earliest whispers of the cosmos. The CMB map reveals tiny temperature fluctuations differences of just a few millionths of a degree. For instance, the slight variations in polarization. How the CMB light is oriented contain clues about the energy scales of inflation and even about gravitational waves from the Big Bang itself. These minuscule differences are the fingerprints of quantum fluctuations during inflation, stretched across the sky. Before that, photons were constantly bouncing off particles in a hot, dense plasma light trying to see through thick fog. But when atoms finally formed, the fog cleared, and light could travel freely. That first light is the CMB. This light has been traveling for over 13.8 billion years today. That ancient light reaches Earth from every direction. By studying the CMB's patterns, cosmologists can decode how the universe expanded, what it's made of, and even how fast it's growing. But it's not just a pretty picture. It's a powerful probe into the physics of the early universe. In this sense, observing the CMB is like reading a message written in the fire of creation, one that tells us not only where we came from, but also how the universe itself was born and evolved. The future of CMB research. What lies ahead? Even though the cosmic microwave background CMB was discovered over half a century ago, it continues to be one of the most important tools in modern cosmology. In fact, some of the biggest scientific missions of the 21st century are still centered around learning more from this ancient light. One of the key frontiers now lies in the study of CMB polarization, specifically a special type of polarization pattern known as B modes. These faint, swirling patterns in the polarization of the CMB are believed to be signatures of gravitational waves produced during cosmic inflation, the ultra-fast expansion that occurred a fraction of a second after the Big Bang. They are exceedingly faint, and the CMB signal is easily contaminated by foreground emissions from our own galaxy, such as dust and synchrotron radiation, neutrinos, the elusive and nearly massless particles that streamed freely through the early universe, leave subtle imprints on the CMB. As CMB photons journey toward us, they are deflected by the gravity of large structures like galaxies and dark matter halos. Every refinement in data, every new satellite, every improvement in theory brings us closer to answering the biggest questions. How did the universe begin? What is it made of? And how will it end? These distortions encode valuable information about the large-scale structure of the cosmos. By analyzing these imprints, scientists can constrain the sum of neutrino masses and potentially answer long-standing questions. In particle physics, that's why future missions are being designed with ultra-sensitive detectors, improved foreground separation techniques, and deployment in extremely clean observational environments, such as the South Pole, Atacama Desert, or even space-based telescopes. If detected unambiguously, B modes would provide direct evidence for inflation and open a new window into the earliest moments of the universe. CMB-S4, a next-generation ground-based project, plans to use thousands of detectors spread across multiple telescopes. To capture ultra-precise polarization maps, LIGHTBIRD planned by JAXA, with NASA and ESA collaboration will focus entirely on measuring the B-mode signal from space, with unprecedented sensitivity. Detecting these subtle signals, however, is incredibly challenging. Upcoming projects like CMBS4, LIGHTBIRD, and PICO aim to take our understanding even further. Another exciting frontier is using the CMB to probe neutrino physics. Even dark energy, the mysterious force driving the accelerated expansion of the universe, may be better understood by studying how it affects the CMB through gravitational lensing. So while the CMB is ancient, a relic from a time when the universe was just 380,000 years old, our understanding of it is still evolving. So here we are after a journey that started with a burst of unimaginable energy 13.8 billion years ago and ended with us, today, listening to its faded echoes across the cosmos. And from this delicate signal, scientists have reconstructed an astonishing amount: the age of the universe, its composition, the seeds of galaxies, and even clues about its ultimate fate. There are tiny anomalies, unexplained cold spots, and hints of phenomena we barely understand. Could they point to new physics, parallel universes, unknown particles? The cosmic microwave background is not just a glow of ancient light, it's a time capsule, a frozen imprint of the universe's baby photo. But even with all we've learned, the CMB still holds secrets. That brings us to you. What do you think the CMB is still hiding? Do you believe the universe had a definite beginning, or is it just one phase in something much bigger? If you could send a question back to the first moment of time, what would you ask? Let us know in the comments. Your thoughts help build this channel into a true community of curiosity, imagination, and science. And if this journey through time and space gave you even a tiny glimpse of awe, don't forget to like this video, share it with a fellow space explorer, and subscribe to Astronomical Library for more stories from the edge of the universe. The cosmos is vast, but with every question, we take one step closer to understanding it. Thank you for watching.